This sequence we're watching tracks a continuous 30-second shot of a singer navigating backstage. Notice the timer. We are looking at a single-pass, fully synchronized audio and video generation, produced entirely in one take by Seedance 2.5. Historically, generative models were restricted to extending brief, stochastic moments. By sustaining a continuous output for a full half-minute, the model can now construct a complete narrative arc, moving through setup, development, and resolution without breaking the shot. This evolution is defined by the organization of space and time. Instead of merely dragging out a static scene, the model links multiple, logically coherent actions and camera movements into a singular cinematic flow. When a system can sustain coherence for 30 seconds, sequence length is no longer the primary technical barrier.
The core engineering challenge transitions from generating enough frames to enforcing strict, deterministic control over the specific events within them. That 30-second limit is a baseline for expansion. Seedance utilizes a multi-round extension protocol, allowing users to append subsequent 30-second blocks sequentially onto existing outputs. As these blocks are chained together, the underlying architecture enforces strict structural consistency. The main characters, their defining features, and the precise geometry of the background environment remain stable across every new segment. Because the system references the preceding visual and audio data, the narrative pacing and the overarching audio-visual language stay synchronized. The viewer avoids the jarring stylistic shifts typically associated with crossing a generation threshold. For creators, this eliminates several layers of manual intervention. There is far less need to manually split disjointed clips, splice them together in an editor, or invent workarounds for broken transitions. By automating consistency across sequential generations, this chaining protocol converts video models into end-to-end engines for multi-minute film production. Giving an AI a longer runway is only productive if it can be steered. To force a latent diffusion model to obey specific rules, engineers must rigorously constrain its available options. This diagram illustrates the model's expanded context window. The system ingests an array of up to 30 images, 10 video clips, and 10 audio tracks simultaneously. Loading this reference array stabilizes complex scenes, routing data to lock in distinct appearances, props, and unique voices. The model interprets this varied input stack to extract precise stylistic elements, like visual composition, lighting, and textures, and applies them globally across the timeline, reducing the system's tendency to hallucinate unprompted details. Front-loading the context window with exact reference material removes the randomness from the process. The model stops guessing what a scene should look like and begins assembling it intentionally from strict instructions. To control physical movement within that scene, Seedance utilizes clay render referencing to define strict spatial priors directly in the latent space. Look at this comparison. Creators block out spatial structure, character motion paths, and camera angles using a textureless white 3D model on the left, and the model animates the fully rendered final output on the right, strictly adhering to that initial physical framework. Because the system now understands the actual geometry of the scene, it can derive highly accurate lighting parameters. It calculates realistic light source direction, adjusts the exact color temperature, modulates the intensity, and maps physically accurate shadow projections.
High-efficiency workflows like this clay render approach are becoming the standard for technical production, a process we document extensively on this channel, so hit subscribe to keep up with these breakthroughs. By injecting spatial priors, developers bridge the gap between unpredictable latent diffusion and highly accurate physical simulation. The 3D geometry anchors the pixels. Once the initial generation is complete, Seedance utilizes timestamp-level editing to apply non-destructive temporal gating across the entire 30-second sequence. This timeline UI demonstrates temporal gating. Users inject text prompts and parameter changes at exact second intervals, altering camera perspective and movement without regenerating the file. During background swaps, the system maintains the main subject intact, recalculating how they respond to new environmental physics. This means the subject inherits contextual physics from the new scene. The exact fluttering direction of clothes, the precise state of their hair, their lighting interactions, and even their gait rhythm automatically adjust to fit the new setting. Tracking the state of a subject and their environment across an extended sequence converts what used to be a rigid one-off generation into a highly composable, professional post-production workflow. This architecture is currently rolling out natively on consumer platforms like Jimeng AI and Doubao Pro, with scalable API access launching via Byte Plus ModelArk. The precision of these models is now being applied to industrial sectors, specifically for the generation of synthetic training data. In industrial simulation, developers use those same 3D structural priors to generate high-fidelity, photorealistic mechanical assembly sequences, perfectly mimicking real-world factory conditions. This highly specific synthetic data is used to train the perception and manipulation skills of embodied intelligence systems. It is also used to simulate extreme long-tail scenarios, like severe weather or complex traffic conditions, for autonomous driving models. Deterministic video serves human creators, but its ultimate value lies in feeding other AI systems that require accurately simulated visual environments to navigate the physical world. Despite these controls, there is a clear frontier limit that the developers acknowledge. The model still struggles to consistently generate physically plausible, complex motions. This photographic reference of a peaking opera performance highlights the mathematical difficulty. When you have multiple overlapping elements, intricate costumes, sweeping flags, and interacting subjects, maintaining spatial coherence and occlusion calculation taxes the architecture heavily. Addressing this instability is the core team's next major objective. They are working to deepen the model's fundamental mathematical grasp of real-world physical laws, embedding those rules directly within the latent space. To achieve true simulation, a model cannot simply arrange pixels that look correct on the surface. It must intrinsically understand and compute the underlying physics engine of the real world. Maintaining strict narrative cohesion for 30 seconds represents a transition point. As sequence length becomes reliable, the focus is shifting from generating raw footage to directing specific physical actions. The technical center of gravity in AI media has moved. We are no longer dealing with stochastic, random pixel generation. The focus is now entirely on precise, deterministic direction. This leaves us with a critical question. What happens to the industries that rely on physical data collection when the cost of infinitely generating accurately simulated environments is reduced to a 3D blockout and a text prompt? We will continue tracking the journey from research paper to working prototype. Thanks for watching Synthetic Labs.